Just like a introduction.
I think like this.
So I guess I can start now. So today, well, thanks for I won't say inviting me. It was kind of a self-invitation, but thanks for organizing these series of talks and putting up with my changing schedule. So I want to talk to you a little bit about some work that I did over the last 6 months. This is joint work with this guy, Paul Kwong. Anybody heard of him before? So if you like this stuff, real performance, writing fast code, he has a blog called Some Lisp. It's here, pvk.ca. You can check it out. That really digs deep into many of these kinds of micro performance issues. And sort of the way this project started is I read a paper that did a series of experiments back in 2003 on their test machine was a Pentium 3 processor. And I thought, well, I wonder if that's still true today, if the results of those experiments are still true today or if things have changed. So I tried to get their code and run it. I did succeed in getting their code. I did kind of succeed in getting it to run, but I couldn't get it to do what I needed to test. 12-year-old C code that was generated using a Perl program just wasn't what I wanted. So I redid everything myself, ran the tests, and got some surprises. And of course, when you get surprises, you want to make sure that that it's not something just specific to your own test rig. So I ran these tests on a series of machines, 5 that I had handy, and the same surprise kept coming up. And then I became really interested in this. First I thought I was just confirming an experiment, but it wasn't at all the case. So then I asked the internet for help. So I posted on Reddit asking for people to run this code on their own machines. I got about 100 responses in the first weekend. And more or less I won't say conclusions, but the results were the same pretty much across the board. And it's in response to this that actually Paul Kwong contacted me, and he was interested in these things. I had already known about him because I'd read some stuff on his blog when researching this, and we started working together. So of course I'm here at Carleton, and Paul works for this company, AppNexus. Anybody heard of AppNexus? Yeah. So it's probably the biggest advertising intermediary in the world. Depends who you ask, but something like 80% of commercial web traffic sees an AppNexus server at some point. So every time you open a web page and some advertisements get displayed, what's typically happening is there's a real-time negotiation that goes on between the provider of that web page, so the person who wrote that web page, and a series of advertisers who are all bidding for space on that page. That negotiation takes place through the AppNexus servers. So these guys care about performance, and that's why they hired Paul Kwong, I guess. Okay. So first of all, binary search. Why do we care about binary search? Well, hopefully it doesn't take too much to convince you guys, but here's just 2 examples. If you look at the Google Chrome code, it's the open source part of it is called the Chromium code base. You look in there and you'll see that there's a C++ method called standard upper bound that actually implements binary search. In that code base, it's called from 135 different locations to handle all kinds of things: cookie handling, GUI layout, graphics, text rendering, video handling, certificate management. So all sort of little, not on huge arrays, but a lot in a lot of places. And don't forget that Chrome has more than 1 billion users now. So this is getting used a lot. So micro improvements in the performance here translate into, well, if you want to think of it one way, you can think of it as savings in electricity across the world, or savings in productivity. If you save a second of everyone's life every single day because your code is a bit faster, well, that's 1 billion seconds a day that you're saving. So that's lifetimes that you're saving. The other example is this AppNexus real-time ad bidding engine that I just described. It runs constantly on 1,500 machines. It handles about 4 million requests per second, this system. And Paul knows this because he works there. 10% of their CPU time is actually spent binary searching a few sorted arrays. So this is, and these are big arrays now. So this is the bigger side of this thing. And if you just do a back of the envelope calculation, let's say with, these are reasonably performing CPUs, so let's say 90-watt CPUs, you'll realize that these things use about 118 million watt hours per year just doing binary search. That's not anything else that the CPU that's happening here. That translates into money. That's about $15,000 of electricity per year just to do binary search. So if you can shave a bit of that off, you'll save there. And of course, AppNexus is not the only company with these giant clusters of machines doing this kind of stuff. So again, you can think of this as saving electricity or saving time. And of course, there's thousands of other examples. Okay. So I'm trying to talk about two things here. One is binary search, and the other is computer architecture. And so here's a picture of what we call the von Neumann computer architecture. It's the way, as programmers, we tend to think about computers when we're programming them. There's sort of two main parts. There's a CPU and memory, RAM. And these two things are connected by a bus. So it carries data from memory to the CPU and sends it back from the CPU to the memory. These things look like this. I have a couple of examples of them here. This is a CPU. So if you've never put a computer together, you may not realize that this is the size of a CPU. When you look inside a computer, you see this big, chunky piece of metal, and you say, oh, that's a nice big CPU. That's not the CPU. That's just the cooler for the CPU. CPU is this big. And memory looks like this. This is what these sticks of RAM look like. They're about this big. And it's worth looking at the sizes. CPU is small, memory is big. And these things usually plug into a motherboard, and that's what has this bus in it. And in terms of distances within the CPU, the distance between the CPU and this memory is actually very far. So the speed of light, the time it takes light to travel that distance is actually a factor here. And that's a big distance. Okay, so that's the way we think of the basic view of a modern computer without any of the extra peripherals, monitors and disks and those things. We won't worry about those. For binary search, they don't come into play. Okay, so the second thing I want to talk about is binary search. So let's make sure we all know what that is, and that we're all talking about the same thing. On what do you use binary search? What kind of input? Yeah.
Sorted array.
A sorted array. So two things. Sorted, meaning that the data in the array is, let's say, in increasing order as you go left to right. And array, meaning that you can access any element of that thing in, I'll say, quickly. So It's not a linked list or anything like that that requires some extra work to access things. If I say I want to look at position 10, it's not a problem. If I say I want to look at position 5, it's not a problem. I just go straight there. And so what binary search does is it tries to locate an item in this array using comparisons. So let's say we wanted to search for 8 in this array. We pick the middle element of the array. We compare that to 8. And in this case, 8 is smaller than the middle element, 38. So what we know is that 8, if it's in the array, is not here, and it's not anywhere over here. So we cancel that out. And now you can think of it as recursively searching or resetting some pointers or indices to say, now we focus our search on this, what's left of the array. Again, doing the same strategy. We pick the middle element. In this case, it's 16. 16 is, again, bigger than 8. 8 is smaller than 16. So we kill that trailing part. Again, we pick the middle element. Now it's 7. 8 is bigger than 7. So we kill that part. And we're left with 9. And 8 is smaller than 9. And our conclusion, that's it, there's nothing left. Our conclusion is that 8 should be there. It's not, but that's what we'll say. And this is actually important. Not only does binary search find the element in the array if it's there, but if it's not there, it tells you where it should go. This is an important feature of binary search. It's why we like it over something like a hash table, which would find it actually much more quickly, but won't tell us anything useful if it doesn't find it. Okay. Code for that looks like this. I'm sorry, to do these kinds of tests, you have to use a fairly low-level language. In this case, it's C++. And just very briefly, the code maintains 2 indices that the answer that we're looking for is somewhere between those 2 indices. In fact, the larger index, called high here, is pointing past the answer we're looking for. So we would never have to go all the way to high. High is either something that's bigger than what we're looking for, or it's past the end of the array, as it is in this case. And then we just do the obvious thing. We compute the middle, what's the midpoint between low and high. We check if x is smaller than that value. If so, then we should throw away everything from the midpoint onwards. If it's bigger than that value, we should throw away everything up to the midpoint, and including the midpoint. And otherwise, if it's not smaller than and it's not bigger than, it must be equal to. So we found what we're looking for. And if you look at this code carefully enough, you'll see that we always return something high, and the thing that we return is the index of the smallest value that is bigger than or equal to what we're looking for. So we're looking for x here. This will give us something that's bigger than or equal to x, and it'll give us the smallest such thing. So in particular, it'll give us the index of x if it's there. If not, it'll give us what would come after it, where x should be inserted. Okay. This is something we analyzed already when I taught some of you introductory programming. Each iteration of binary search, where we pick an element and compare it, and then either adjust low or high, you can check that it either terminates because it found what we were looking for, the middle element is the element we were looking for, or the range high minus low decreases by a factor of at least 2. So we cut the array in half each time, at least in half. So if we start out with an array of length n, then we will finish, this process has to finish after log n iterations. So that's really what log n means, is the number of times you can cut n in half until you get down to something smaller than 1. Another way of thinking about that, and this is the way I want you to think about this when I show you the next slide, is that if I double the size of the array, then that binary search only has to do one more iteration. So think you make the array twice as big. Binary search is going to look in the middle of that thing. So after one iteration, it's cut it down already to the original size. Okay, so what does that look like in terms of running time for binary search? Well, here I've plotted the time to do 2 million searches on an array of length n. N is here on the x-axis, and you'll notice that these numbers on the x-axis are powers of 2. So this is not a linear scale, this is a log scale, and so with the explanation that I just gave, this basically says, you know, each time I double the size of the array, there should be one more iteration, which means that, you know, as I go from 2 to the power 4 to 2 to the power 5, there should be just the difference should be the cost of one more iteration. From 2 to the 5 to 2 to the 6, that should be the cost of one more iteration. So when I use a log scale on this axis, I should get basically a line in the running time of this thing. And this is pretty good. There's 2 plots here. One of them is the code that I just showed you, which I call branchy binary search. And the other one, the green one, is the code that you get in the C++ library that comes with GCC that implements binary search. And these are pretty close match. Our code is a little faster, probably because we don't have to handle some edge cases, or we don't carefully handle some edge cases. Yeah?
Did you look into that the bump that's in both of them?
Yes, I'll tell you that at the very, very end of the talk. I'll explain what's happening there. It's not an accident. It's not just that the process is that something else was happening on the computer when that experiment ran. Okay, so any questions so far?
In these applications, why do they need predecessor and successor?
I don't know. For some, yeah, I don't know. I never looked carefully at the code. But they do know, these people do know hash tables, so they would. Here's something not so interesting. If you compile that code that I showed you, and you ask the compiler to output assembly language, this is what you get, except without these helpful comments here. These are my comments. And this is why this code is called, I call it branchy binary search. So don't worry if you can't read assembly. Just a few things to note. There are these labels here. So those are labels that represent a place that the code might jump to. And you'll see them, they appear, for example, here, any instruction that starts with a J is a jump instruction, meaning that that instruction, when it executes, it may jump to that location in the code. So from right here, from this instruction, you may jump directly to line 5, which terminates. And that instruction, what's it doing actually, if you decode all this, you'll realize it's testing if low is equal to high, which was the termination condition of that loop. So if you start out in low equals high, which could happen if your array is of length 0, for example, then this jumps right to the end and outputs 0. Right here is the top of the while loop, so there's a label there because it keeps jumping back up to there. And then you can decode all, decipher all this and say, here is, we test if the middle element is bigger than or equal to x, and if it is, well, here's where we test it, and then here's the thing that says if that test was not, if a at x is not bigger than x, then jump to line 5. So there's a bunch of jumping around in this code. It doesn't translate exactly into the structure of the if statements, because the compiler thinks it knows a better way to do that, but it implements exactly the same logic. So the key point is there's lots of jumping around here, lots of these jump instructions. Okay, so binary search is, we love to say this in algorithms courses, it's optimal. And the argument for that is, well, the result of the search has something like n+1 possible outcomes. The algorithm only makes binary decisions, and so we need to make at least log of n+1 of these binary decisions. So what does that mean? Well, actually, optimal here really says it does the fewest number of comparisons that it could possibly do to solve this problem. The real question is, are comparisons actually that expensive? Is that the most expensive thing this code is doing, or is it something else? Well, to know that, we have to look a little bit closer inside one of these things. Okay, so this is a Xeon processor. It runs at 3.3 gigahertz, meaning that it actually it has a clock that cycles 3.3 billion times per second. And it's doing its best to execute an instruction during each of those cycles. So it's trying to execute 3.3 billion instructions per second. Right now it's not trying that because it's not powered, but if it was, it would be. Problem is, executing an instruction is a sort of complicated thing. There's a lot of things that have to happen. First thing you have to do is you have to fetch the instruction. You got to get it and fetch it. You actually have to decode it. Internally, these things use different representations for instructions, so you decode it. If the instruction wants to use the contents of some registers, you have to fetch those registers. Then you do what's properly executing the instruction. So for example, if the instruction says, add these two registers together, or the contents of these two registers together, well, you have to send the contents of those registers off to the arithmetic logic unit, which will do that addition operation. And then finally, when that's done, the value that comes back from that usually gets stored in a register or in memory, so you have this final stage of memory access. And you can't do all this in one cycle, one clock cycle. So the solution is to treat this thing like a pipeline. And this is something that happens repeatedly in computer architecture, is we have this great manufacturing processes that can make tiny, tiny things and cram lots of stuff onto this tiny chip, but we can't really get around the problem of being able to only do a tiny amount of work in one cycle. So the thing we do instead is we try and do a lot of work in many different things in different places on the chip at the same time. So this is just a few instructions from the code that I showed you earlier. So actually, what happens is there's a pipeline that these instructions get shoved into. And while this instruction here, which is a move instruction, which is taking stuff from memory and putting it into a register, while it's finishing up putting that stuff in this register, the next instruction, which is supposed to execute, is actually executing. It's over in the arithmetic logic unit doing whatever it is it's doing. Anybody know what that's doing? Yeah.
XORing the two and putting it, well, it's basically setting it to 0.
Yeah. So it's computing the exclusive OR to the contents of two registers, but it's the same register. This is actually a fast way of setting a register to 0. And while that's over being executed, this one is being decoded, and its registers that it needs are being fetched. And while that's happening, it's fetching the next instruction. There's another part for fetching the next instruction. This figure didn't come out very well, but this has all these parts about instruction decoders. There's registers, the arithmetic logic unit, and all that stuff. These are different parts of the chip, and they're all doing different things for different instructions. And then tick, the clock ticks, and everything moves up to the next stage in the pipeline. Great. So now that XOR instruction gets to put the results back. It sets that register to 0. That other instruction gets what's called a retire. It's finished. This guy gets to execute, and so on. But now something funny happens. This instruction that we just fetched here, it's a jump instruction. It says, well, there's a comparison that happens here, and if the result of that comparison is bigger than or equal to, then we should jump to line 5. Otherwise, we should just execute the next instruction in the list. That presents a problem now, because when the clock ticks, we don't know what to do. Because after this jump instruction executes, we're either going to be at line 5, or label 5, or we'll be doing whatever the next instruction was in the list of instructions. So the processor doesn't know what to put in the pipeline. And it does its best. It just makes a guess. And there's very sophisticated, well, actually not that sophisticated. There are algorithms that have been tested for a long time, over a long period of time, that try and predict the outcomes of these things, decide whether it's going to jump or not. They're mostly based on statistical data. So if this jump has executed 25 times in a row already, and it actually took the jump, then it's going to guess that it's going to take the jump again. But they're a little more sophisticated than that. They can even figure things out, like if it goes every second time, it'll actually correctly guess. It'll learn that and correctly guess. But it has to make a guess. And if it guesses wrong, that means there's an instruction now moving through the pipeline which should never be executed. And eventually we'll figure that out. Eventually this thing will get to execute, or at some point we'll know whether this condition is true. And if it's wrong, then all that work that the pipeline did up until that point is wasted, and what happens is what's called a pipeline flush. Everything after this thing will get flushed out. And I drew this pipeline as having 4 stages, but actually there's, in let's say modern Intel processors, there's actually 20 to 24 stages. So that's 20 to 24 cycles of these cycles that happen 3.3 billion times a second. That's expensive, right? The processor is doing its best to execute 1 instruction per cycle. Occasionally, if you get a pipeline flush, you may have to throw out 20. You may have to waste 20 of these cycles. That's really bad news for binary search, because if I'm doing binary search and I'm searching, let's say, for random things, there's no good predictor of whether this is going to be less than or bigger than. There's no statistical data that's going to help. Half the time the search goes in the first half of the array, half the time it goes in the second half of the array. So there's no good branch predictor, which means it's going to guess wrong half the time. Which means, and you saw the amount of instructions there. There's like, and this pipeline is 20 to 24 of these things. So this processor is going to be digging ahead, running this code, putting it in the pipeline in advance, actually a few layers branching ahead of time. Half of them are going to be wrong, and it's just going to keep chucking those out. This is a problem that's been known for a long time, that branch misprediction is expensive. And so one solution is to try and make better branch predictors, but another, when there is no good way to predict a branch, which is the case with binary search, is to just eliminate branches. So there's instructions that have been introduced that kind of cheat. They're called predicated instructions. And the main one that you see on Intel machines is what's called a conditional move. And a conditional move says, it's like an if statement and a move all at once. It'll say something like, take this data and put it in this register, but only if something is true. Okay. So why does that help? Well, because that instruction executes, and it may or may not put this stuff in this register, but at least you know what the next instruction is it's going to execute. It's the one that comes right after that. There's no jump or anything. And so the pipeline is happy. It gets to shove the next instruction in the pipeline. There's no decision to make there. Now, this is an assembly language instruction, and we're trying to get a compiler to generate this using C++ code. This is where Paul Huang comes in really handy. He knows how to do these kinds of things. This is another version of binary search that does its best to reduce the amount of branching. And don't worry too much about how it works. It basically doesn't use this high-low idea. Instead, it maintains a pointer to the first element in the search range, and it maintains this counter n, which tells you the length of the search range. So one trick that it uses is it always decreases n by the same amount. It always cuts it in half. So that means that there's no branch that has to happen there. And another one that it uses is this little bit of code here. Remember, so there's a pointer to the first element that you're searching in, first element in the search range, and the length of the search range. And if you are, if the element you're looking for is bigger than the midpoint, then the new place you're looking is just past the midpoint. In fact, in this case, it sets it to the midpoint. So this is a line of code that says, if the midpoint is smaller than the element you're looking for, then change the base. So reset the base to be this midpoint. Otherwise, leave it unchanged. So this sounds exactly like a conditional move, right? If some condition is true, that's this condition here, then take this value here and move it into this variable base. Otherwise, don't change it, just set it to its same thing. Compiler recognizes that, and it just can't resist using a conditional move. And this is the code you get from that. There's that conditional move happening right there. So notice there's many less labels in this code. In fact, there's sort of the minimum label. This is the top of the while loop, and this is the convenient place to exit in case you need to exit right at the beginning of the line. So the code always just does straight through and back to the top, straight through and back to the top, straight through and back to the top until n is smaller than 1. So, is it faster, do you think? Certainly more elegant. What's your guess? So who thinks this code is faster than the branchy code? Yep. Okay. And who thinks that it's slower than the branchy code? Okay. And then there's a whole bunch of people who have no opinion on the matter. Well, there's the result. This is the code I just showed you, the branch-free code. And this is the branchy code. So actually, when you look at, when you consider that there's an overhead in just testing this code, this thing actually runs in less than half the time of the branchy code. I mean, it should, right? I mean, it's avoiding these pipeline flushes that take 20 to 24 cycles. So it should definitely be faster. So those of you who said it's faster, congratulations. So good. So now binary search is optimal. It does the fewest number of comparisons possible, and the branch-free version makes no branch predictions. Is there anything else we need to worry about? Any other aspect of computer architecture that might get in our way here? Well, let's see. There's what's called the memory hierarchy. So again, if we look inside here, we saw that there's a pipeline, but there's a lot more inside that CPU. Actually, usually inside the CPU, there's more than one processor. That's not going to be an issue for us. We're only doing binary search on one thing. But there's this whole level of what are called caches. And remember, these things, compared to the distances inside here, the memory is miles away from this processor, really far away. It takes a long time for electrons to travel from this thing to that thing and back again. And so that really means that accessing memory is slow, and computers try and reduce the number of accesses needed. So inside this processor, it has a whole bunch of different levels of its own memory. It has what's called an L3 cache, which can hold a whole bunch of data that's in RAM and keeping it closer to the processor. That's usually shared among all the cores, and then each core also has a couple of levels of cache as well. So for example, just to give you an idea of the sizes, RAM you usually measure in gigabytes, right? There's L3 caches, they're usually a few megabytes. The L2 caches are a couple of kilobytes, and the L1 cache is also measured in kilobytes, or sorry, hundreds of kilobytes for L2 and a few kilobytes for L1. And if you look at the relative speeds of these things, accessing something from RAM, that takes about 100 cycles. From the L3 cache takes about 40 cycles, from the L2 cache takes about 10 cycles, and from the L1 cache it's about 4 cycles. So really big difference here, right? It's a difference between 4 cycles and 100 cycles. And this 4 cycles is really not an issue, because we saw that the pipeline is like 20 cycles deep. And so as long as we start fetching early enough, the data will be there when we need it. But 100 cycles is more than the length of this pipeline. So let's go back and look at this again. We know that now we know more about computers, that there's these caches. So maybe these come in and have some effect on this. So here's our very fast implementation of binary search again. It starts executing, it does sort of what we expect. Here's where we hit the limits of the L1 cache at this point. So up until this point, the entire array we're searching can fit in the L1 cache. And after a few searches, it's all in there. And then we have to kind of dig our way into the L2 cache. That doesn't really seem to have there's maybe an increase in slope there. It's hard to say. But if we go back, what did we say? The speed of the L2 cache was about 10 cycles, so the pipeline can still hide that. But then we make the data a little bit bigger, and we run out of L2 cache, and in this range here, we need to start using the L3 cache, and there's a big increase in slope there. So now, every time we double the size of the array, we have to do one more iteration, and that's an iteration that needs to go all the way down to the L3 cache, and we see the cost. I mean, there's a huge spike in slope. And what happens when we run out of L3 cache? So what I just showed you was the picture up to here, and now once we hit RAM, it looks like this. Okay. All right. So you may say, well, fine, but that doesn't mean, that's just, once the data gets too big, then this thing is slow. We still have a good implementation of branch-free binary search, but we can go back and retrospectively say, well, what about our old implementation? How does that affect this thing? Well, there's our old implementation of binary search. Yeah, before the picture that I showed you stopped here, and we saw that this thing was much slower, this old implementation. But once you extend the picture out a little more, it's actually getting quite a bit faster. So if you guessed that the first implementation was faster, you're right as well. So everybody's right except those who didn't make a guess. Okay, so this confounded both of us. So remember I explained a little bit about the history of this. That lousy code, this lousy blue code here, is the code that I wrote initially. And then Paul got a hold of it and he wrote this red code, this nice branch-free code. And that depressed me because his code was so much faster. And then I did this whole chart, and then I was happy again. But we both had no idea why this was happening. This was not at all clear. I'll explain it to you now, but it took us a while to figure this out. So I told you all of the pieces you need to know. And we knew all these pieces, but it still took us some time to figure out. So remember that branchy code. It has this issue that it keeps having to guess whether a branch is going to be taken or not, and it can't really do much good. There's no good way to guess because half the time the branch is taken, half the time it isn't. There's no pattern. So it just makes some guess. Half the time that guess is wrong, and it's going to have to go back and undo all the work that it did from that point onwards. That costs about 20 cycles or so. That's expensive. But half the time the guess is right. And if the guess is right, then as soon as one of these instructions, eventually that means that there's an instruction that enters the pipeline that asks for the middle element, the middle of some range of the array. And as soon as that instruction enters the pipeline, and these processors are smart, they see that this is an instruction to load a memory address. They immediately say, okay, memory system, go to work and get me that thing, because I want that to be there by the time I need it to really execute this instruction. So it guesses right half the time and immediately puts that thing to work. On the other hand, the conditional move, it does this conditional move. It says if this condition is true, move this thing into this register. That doesn't happen immediately, and because it doesn't know whether the condition is true or not. But almost immediately after that, it says whatever is in this register, go fetch that memory location. And then the processor really doesn't know what to do at all because it doesn't know what's supposed to be in that register. It just stops completely. And it waits 100 cycles for that thing to complete and then loads the memory location. So this branch prediction actually works in our favor, even though it's wrong half the time. So when it's wrong, it costs about 20 cycles, but when it's right, it cuts off a lot of cycles. So that's where we save here. Now I don't like this situation of having two different algorithms and some switchover point. So the question is, can you get the best of both worlds? And the answer is yes, but you have to know a little bit about the instructions that are available to you. This is just the code for the branch-free binary search that I showed you, with two additional instructions added. These you've probably never heard of them before. They're called prefetch instructions. And a prefetch instruction says, I think I'm going to want this memory address soon, this memory location soon. Please start fetching it now. What are the two things that we're prefetching here? Well, before binary search looks at the middle element of the array, we ask it to prefetch the element that's 1/4 of the way through the array and 3/4 of the way through the array. Then no matter what happens here, that is the next element that we're going to be looking at. One of those two is the next element that we're going to be looking at. So we tell it to fetch both of them now, then we do our comparison, and then it's there sooner when we need it. Okay? And that is this orange curve here in these diagrams. So it is values of n for small arrays, it's nearly as fast as the normal branch-free code. There's just these 2 extra prefetch instructions. And then for large values, it's faster than all of them. So just a quick schematic, just so you really understand what's happening here. The branch-free code is chugging along, doing this comparison, and then it tries to do another comparison. That's what would happen in this point in time. But whatever it wants to compare with is just not ready, so it waits for the memory system to come, and then it can finish that comparison. Same thing happens in the next stage. It waits for the whole memory system, so on. The code that does prefetching is much more difficult to understand. In fact, if any of you have seen this movie, what's it called? Time travel movie. Tommy knows the name. Primer, yeah. If you've seen the movie Primer, sometimes these things can be as difficult to understand as Primer. No, nothing is that bad. Yeah, so basically what happens is we say, okay, memory system, go get those 2 things for us. Then we do our comparison. Memory system is doing that while we do our work, and it comes back just that much sooner. We still get stuck for a little bit, but the results come back sooner than they would otherwise. Okay. So a couple of things to note here. The processor and the memory system work in parallel. They're miles apart. Why shouldn't they be able to do things at the same time? And the memory system has its own pipeline. Notice here, we actually load twice as much stuff from memory as we use, right? We load both those memory locations. We only use one of them. That doesn't seem to bother the memory system. It's happy to do that. Okay, so that's the story so far. You have this long processor pipelines. They need branch prediction. They need to do branch prediction to keep the pipeline full. And when they make mistakes, that's expensive. Sometimes you can avoid these mistakes using conditional moves, so just avoid the branches altogether. But also, memory is this hierarchy with different levels. And if you think about it further, you think, well, if I run out of RAM, what happens? Maybe you go to disk. Well, what happens if I run out of disk space? Well, maybe you have to fetch things off the cloud. I mean, you laugh, but this is not. This is true. There's this thing, and then maybe you have to send it off to Mars at some point. The memory subsystem is aggressive. It tries to, as soon as it knows which data that it wants, it's going to need, it gets it as quickly as it can. And if we're smart, if we know what we're going to need, we can ask for it explicitly. Or if we don't want to be smart, we can just not try and optimize our code so well. So take that, Paul, and just write branchy code. And actually, branchy code is an implicit form of prefetching. So branchy code with this speculative execution is basically implicitly prefetching stuff for us. And what we learned here is that these 2 things interact in weird ways that are very unpredictable. So if you just focus on optimizing this one, you can run into problems with this one, and if you just focus on optimizing this, well, you run into problems there. So there's no obvious, not immediately obvious wins. You have to think of both of them at the same time. Okay, so that was 54 minutes. That's probably enough for you guys. This is just like the beginning of this paper.
Did you say we were going to explain the bump at the start?
The bump.
The bump, okay. I'll skip to the end and explain the bump. There's a bump. And this is a really interesting thing. So what do we see here? This is just the running time of branch-free binary search, starting with somewhere around 2 billion. So I think right around not 2 billion, but it's actually 2 to the power 31 is this thing here. Where this peak is 2 to the power 31. And then there's just a little bit, go a little bit off to this side, a little bit off to this side, just to show you the bump. And what's happening there? So why does it get suddenly so slow when you reach this power of 2? For that, you need to know a little bit more about the cache and how it works. So where are my markers? So when you ask for a location in memory, you specify some integer, right? It's just the location is an integer in memory, and an integer is just a bunch of bits. Okay, so one thing that we didn't get to is that actually the memory is broken up into cache, what are called cache lines, and these last 6 bits of this address, they don't matter. They don't, everything, it doesn't matter what you put here, you're going to get the same cache line from memory. That's not so important. But what's the bigger thing is you have this L3 cache, and it's big. It's 8 megabytes. Okay? And what is it doing? Well, when someone provides one of these addresses, it has to solve the following problem. It has to say, is this address, this memory location, is it stored in this cache, or is it not, in which case I have to go here to RAM. Okay. So this thing is storing a whole bunch of memory locations, and we're basically asking, is this memory location stored in here? Well, I mean, this sounds a lot like the problem we were originally trying to solve, right? We are searching in an array. This is a big array full of data, and we're asking, is this piece of data in this array? So internally, this thing is trying to solve a very similar problem, and 8 megabytes is a lot of data to have to look through or somehow search on for every access. And so what happens is this thing cheats. It can't really do, it can't really solve that problem in its full generality. Instead, what it does is it takes these bits of the address. So for 8 megabytes, I don't know, that's like, there's 23 bits of the address here. So it takes these 23 bits of the address, and it says, if this piece of data is in here, it's going to be at the location pointed to by these things. Okay? So it'll be at this location. That's the only place that I will be allowed to store this piece of data. And so that makes it easy to find, right? You just look there, and it's either there or something else is there, in which case you say yes or no. Problem is, if some other address comes along that is very, very different, but happens to be the same just in these bits, then it's going to say, well, I want that location now. Okay. So these bits actually tell you where in the cache this thing is allowed to live. And if you take 2 different addresses, so that happen to agree just on those bits, they can't both be in the cache at the same time. Fine. So that says if these bits are the same, these 2 things can't live in the cache at the same time. Now, let's say we have this big array, which is what's happening here. And this array has size, nearly exactly 2 to the, what did I say?
31.
No, it's only 20, it's 2 million, 2 to the 21. So it has size 2 to the 21. So we look at the middle element. So that middle element is at index something like 2 to the 20. So what does 2 to the 20 look like in binary?
1 and 19.
So 1 and a whole bunch of zeros. Okay. So the cache, the L3 cache says, is that in there? Well, if it is, it'll be at this location here with all the zeros. Okay, maybe it's there, maybe it's not. Next thing we do is we go either left or right on this thing. So let's say we go left. Well, this is now 2 to the 19. What does that look like? Well, that's a 1 and a whole bunch of zeros, just one less zero. But when we send this down to the cache and say, is this available for us? It says if it is, it's at position 0. And actually then we realize, no, it's not going to be available for us because the thing we just loaded is at position 0. And now it's going to go to RAM, it's going to take that thing and put it up at position 0. And so we totally, each step that we take, except for the last few, until we get this 1 all the way down here, is not going to, the cache does not help at all. In truth, the situation is not quite that bad. It's more like these guys who all have zeros here, they get to choose like one of 6 locations or maybe 8 locations in the cache where they can live. So you can squeeze 8 of those guys in there, but no more than that. And well, actually for this kind of thing, we would need like 20 of them. So we run into problems. And as soon as you have more than 8, you already run into this problem of eventually by the time you get to the end, they've all been booted out, and it's like they're all sharing the same spot. So powers of 2 and binary search do not mix well. So go to Paul's blog, pvk.ca. You can read a nice article about how to deal with this that involves using not binary search, basically 3-way, splitting something like 2/3 of the way into the array instead. Okay, I think that's probably a good place to stop for today.
Would you like to come back Monday?
Whenever you guys will have me back.